All right, good morning. Cool, how is everyone? Or how are you? Yeah, I'm pretty tired too. I'm getting more sleep, but I'm getting more tired. And I actually think there's like allergens or something out there because I know a lot of people who are just really run down right now. Or it could be recursion in physics, I don't know. Um, any any questions up to here? Yeah, all of the above, definitely. So reminder, PA5 was pushed back until Tuesday. So despite what the grading rubric says, PA5 is due on Tuesday morning at 8. Um, and your SLP presentations are Monday at 10 o'clock during class time. I will post an announcement on Canvas later today with details, but you'll basically be going into a different Zoom room, and I'll post the link for that. Um, Usual class time, 10 o'clock, show up, hop into the Zoom room. Do not put yourself in a breakout room though. I will put people into breakout rooms. If your Zoom name is not one that I recognize as being you, then I'll probably send out a chat and say, hey, is so and so here, um, and we'll go from there. But it'll basically be that'll be our whole class on Monday. Will be you doing presentations, and there'll be 3 to 4 people in a room, and you'll basically just take turns doing your presentation. 5 or 10 minutes, right? And theoretically, visitors will come and go and enter rooms. They'll have a list of who's in what room with what topics, and they'll just kind of pick and choose and pop in and pop out. They might ask you questions, and I'll just kind of be wandering around from room to room also. And we'll see how this goes. We haven't done this before with an online presentation, so we'll see how it works out. So if you look at the sample output for PA5, in the beginning of the program, it shows you the contents of your knapsack file, right? So item 1 is this, it weighs this much, it's worth this. Item 2 is this, it weighs this much, it's worth that. So just echo that content out in the beginning of your program's output. And I'm not being super picky about the format of that. Do you have to have a camera to show how your project works? It's up to you. It depends what equipment you have, and it depends what you're hoping to do in your presentation. So, you should have that poster that you submitted for your final upload, so you can share that and talk behind it. If you have code or something, a website, something that you've developed on your computer, you can screen share and use that as part of what you talk about. If you have something physical and you want to show that and you have a camera, right, you can put the camera on that. If you want to, do a formal presentation with a camera on you while you stand in front of a copy of your poster and talk, that's fine. Pretty much whatever works for you. And you'll at least be presenting to the other people in your group, and I'll be going around from room to room as much as possible, so will Izad, but there should be other people coming by from throughout the school. This was sent out to a campus-wide announcement, presentation date and Zoom info, so other people may pop in and see what STEM students are doing, so presenting for them as well. So I'm going to suggest that you simply take turns with everybody in the room going through kind of a full presentation, right? 5 to 10 minutes. and just do it round robin style. So, you know, one person does their presentation, next person, third, fourth, and then go back to the first. Um, it's, you know, probably 40 minutes at the most by the time we get things set up. Um, so, you know, if it's 5 minutes per uh, presentation and there's 4 people in the room, you get to do 2 presentations basically. Um, but, you know, if somebody is asking you lots of questions, or you're very excited about what you've done, you might, you know, talk longer. Um, so it's pretty informal. You definitely have 5 minutes of material. Once you start talking about stuff, time goes really quickly, right? And there's no requirements here, right? It's not like you need to, you know, present a theory section and a background and a competitive analysis. We've got these sections on the poster, but really this is your project, this is your presentation. So, you know, if this is something you're passionate about, which hopefully, you know, that's how you helped pick the project, um, just, you know, talk about it. What have you been doing with it? What are you hoping to do with it? Why are you excited about it? Where would you like to take it, you know, in an ideal situation with lots of resources available? And, you know, kind of go like that. Should we have something rehearsed? A lot of times, most of the time, when I'm talking about something, I like to rehearse it, just to kind of, you know, ease my nerves, so that I'm not, you know, facing the, like, what should I say? How do I start? You know, um, just, you know, I mean, grab a pillow and put it in a chair and talk to it about your project. Um, but, you know, doesn't have to be like polished. You don't have to have, you know, like some sort of professional presentation or something like that. Part of this is, you know, part of the SLP is practice in talking about your work and presenting to other people and so on and so forth. Um, so you can practice or rehearse as much as you think will help you be more comfortable. Yeah, rehearse to your pets. I had a cat once who knew like lots of mathematics. See, so what I'm getting here is that this is a hyper-graded professional presentation. Yes, we will have Fortune 500 CEOs critiquing you. Um, or as one person said one year, you know, they're going to live stream this to all of your parents. So yeah, pretty low key. The presentation in spring tends to be a little bigger. One, because people are more likely to have, you know, something closer to a finished product, and two, you know, that's kind of the culmination of a year's worth of work. So that one, you know, sometimes we've had people from the newspaper show up, sometimes we've had people from industry come by and see what's coming out of Clark, you know, stuff like that. So that one gets to be a little more exciting. And of course, you know, when we're doing this in person and you've got a room filled with people walking around, looking at things, talking, it's a pretty um, high energy event. This one I think is going to be more low key because, you know, Zoom. But I think it'll be good. As far as I know, the one in spring will probably be online also, unless by then things have significantly changed. Clark is, you know, as you know, continuing with their online modality for spring with a few exceptions, and gathering a bunch of people in a small space for a couple of hours, probably not a really good way to re-enter into a face-to-face setting. So I'm guessing we'll still do this online in spring, um, which is unfortunate, all things being equal. Summer has already been decided is going to be online also, and they're currently trying to decide about fall. And I honestly don't know which way fall is going to go, but you know, a lot of you are going to be WSU or somewhere else by fall. But I don't know what their decisions are going to be either. As you know, things are starting to open up, but hopefully that's good timing. We have to see where things go. I do miss being face to face. I mean, I miss being in the classroom. I think there's a lot better potential for, um, engaging with the material and with each other in a face to face setting. And Zoom is, better than nothing, but it's fairly detached at times. So I'm kind of hoping we're back to the classroom in fall. Interesting. So the person you talked to at WSU said they're leaving fall up to the professor? Because I know spring is fully online, and I hadn't heard yet about fall. Um, but yeah, flexibility is good. Yeah, I'm tired. I thought you said I no longer have to account for time travel. I was like, really? But yeah, for travel time. Yeah, that definitely helps. And time wise for me, it's actually working well being here because I can do my office hours and I can kind of close my door, 15 minutes before class, which usually lets me get here on time. And I can't do office hours in person right before class because inevitably, I've got people coming in like 1 minute before class starts, and I hate to send them away, so I end up coming into class late. Yeah, counting for time travel can be tricky, definitely. Got to keep that in mind. All right, let's talk about dynamic programming. So, any questions on PA5? Let's start with that. So if you've got your basic max val working or close to working, right? That's normally a function that returns an integer. So you give it a capacity, it gives you back the maximum value you can get. If you're ready to move to working with the inventory count, right, the number of each item that you want, you can make yourself a structure. So let me just call my structure answer. And answer might have the following pieces. It might have a maximum value piece, which is a thing that we're already returning from max val. And then we might want an array of item counts, so we could make item counts. An array of 128 integers. And you want to initialize this to 0. I'll let you figure out how to do that. And then instead of saying that max val returns an int, you can just say it returns a struct answer. Right? Don't make it a star. If you make it a star, then you have to do a malloc, and then you have to do a free, and so on. And we don't need a whole slew of these answer objects, right? We just need one of these that we're declaring as the return value from max val. And then inside your for loop, right? So you can do something like, best val equals 0. And you could make a struct answer best answer. And then each time that you do this recursion, right? So we're going to say, okay, well, you know, if I start with item 1, I get a value of 2 and I get the max val of 5. So you need to call max val 5, and max val 5 is going to return to you all of this information, the maximum value and the item counts. So we could have a struct answer best answer, and we could have a struct answer this answer. And initialize your best answer to 0. So this is like initializing your maximum value integer variable. And then, you know, for each item, you can do something like this answer equals max val, right? Diminish the capacity by the weight of item I, find the maximum value of that, and save what max value gives you back in this answer. Okay, this answer is this piece of information, the maximum value and the item count. And if this answer's value is better than your best answer's value, right, then you want to set your best answer to this answer, and you want to increment the item count of whatever item you're on, item I. You want to increment that count by 1, so you just bump up best answer dot item count bracket I. So it's alphabet soup trying to describe that in words, but the concept is, you know, what we were doing here. So my best answer is 17 because that's better than 0, so I'm going to record in a temporary spot, you know, the value 17 and the count 101, where I bump this up by 1 because I'm taking in an extra item 1. And then when I do this calculation, I'll see that the value I can get is 18, and that's better, so I'll record my best value is 18 and my item count is 010 with this count bumped up by 1, so 020. And then I'll call this case, I'll calculate max val 2, add that, I'll get 17. That's not a better answer, so I don't change my best answer. When I'm done, my best answer is 18 with an inventory of 020. So you don't need to be passing around these structures, you don't need arrays of these structures, you don't need to dynamically allocate these structures, you just need something that's kind of like a super duper integer, right? Instead of just an int, it's an int plus an array of item counts, and just pass that around from you know, when you call max val, get that back, use that as your best answer, and so on. All right, not seeing any questions on that. So that's either crystal clear or too muddy to even ask about. Hopefully the former. All right, any questions on cutting up rods and selling the pieces? Our example that we were doing yesterday. So let's look at some other examples. So longest common substring is another one of these problems that we can describe as solution in terms of the solution of smaller problems. And so here's the setup. Suppose we have two strings. A, B, C, D, E, F, G, and All right, so two strings. And the goal of this problem is to find the longest collection of letters, an ordered collection of letters that's common to both strings. And they don't need to be consecutive, but they need to be ordered. And so, for example, here's an A, here's an A, here's a C, there's a D. I don't see an E, but I do see an F, and I see a G. So there's a common substring between these two, A, C, D, F, G. There's another common string, which would be A, followed by B, followed by D, followed by F, followed by G. That's another substring that's common between these. And both of those strings had 5 characters. And maybe there's a longer string somewhere. So for example, here's an A, and here's an E. So that's another common substring. So the question is, what's the longest substring in common between these two strings? And it's a hard problem to solve. It's an easy problem to write an algorithm for, but that algorithm is going to be very expensive computationally. It's a hard problem to solve efficiently. Because, right, we're not, if we were looking strictly for this exact string in here, that's pretty straightforward. First we look for an A and we see if it's followed by a B, and it's not, so we go back and we look for another A. There's an A, it's not followed by a B, right? So looking for one string in another, very straightforward. It's an order n operation, basically. Looking for a substring of this in here, still probably order n squared, right? Basically look for this string and then look for that string and so on. But since these don't have to be consecutive letters, right, this gets combinationally pretty large. And this is a real life problem. This pops up in bioinformatics, for example. If you have 2 strands of DNA, when you sequence these things, sometimes you get other things in between the relevant base pairs. And so we'd like to find, you know, a subsequence of this that's also a subsequence of that. But we want the largest one possible, right? And we might do this to compare genetic sequences of 2 organisms, right, and see what the degree of similarity is in their base pair combinations. So this is a bit of a real world problem, and it lends itself really nicely to this kind of recursive approach where we basically break it down into subproblems. So let me show you an algorithm for tackling this. And this is going to be pseudocode because it's actually pretty ugly to try to code in C. So I'll pretend we have like string operators in C. So let's find the longest common subsequence of S1 and S2. And the goal to doing this kind of algorithm is to basically find a way to express the value of this function in terms of the values of functions on somehow smaller arguments, so that as we recurse, we eventually hit an ending point. DNA is a data structure in some way. DNA is freaky. So we have this common subproblem aspect, but we also have this idea that the subproblems are somehow smaller than the original problem, so that our recursion isn't infinite, so that it ends at some point. So here's how we can break this problem down. There's 2 possibilities. If S1 and S2 end with the same letter, so let's say this ended with a G, then whatever substring we find in common between this and this, whatever substring we find in common between this smaller string and this smaller string, if we take that longest common substring and we just tack a G on the end, that will be a substring of this and this. So if S1 and S2 end with the same letter, return 1 plus the length of the longest common substring of S1 minus the last letter, and S2 minus the last letter. Minus the last letter, I mean take off that letter. So if S1 and N2 have the same letter at the end, find the longest common substring on the truncated strings, or we've thrown away that last letter, and then just add 1. Because whatever the longest common string is between these, we can take that string, add a G to the end, that will be a common substring between the original strings. Does that make sense? Silence open to interpretation. I will continue, but ask questions. Okay, so if they end with the same letter, find the longest common substring on the shortened strings and just add 1. Otherwise, they don't end with the same letter. So they ended with, say, an F and an E. Alright, so whatever the longest common substring is, there's two possibilities. That longest common substring could include this last letter, but we know that's not going to be the last letter of this string. So if the longest common substring includes this last letter, it's also the same longest common substring between this original string and a truncated version of the second string. Because since this is not the same as that, removing this last letter is not going to change the solution. Alright, so in this case, the last letter is not the same. There's two possibilities. One, the longest common substring between these two is the same as the longest common substring between these two, where I've removed the last letter of this. But it's also possible that the LCS between these is the same as the LCS between these, where I've removed the last letter of this first string. But the LCS between these is guaranteed to be the same as one of those two cases. Right? If it wasn't, it would mean that these last two letters were the same. So here we can return the largest, or the larger, of the longest common substring of S1 minus the last letter, S2, or the longest common substring of S1, comma, S2 minus the last letter. And that's a complete recursive way to describe the longest common substring of two strings. And this takes some contemplation for it to really click. But it's a very recursive way of thinking about this problem that would not necessarily occur if someone just said, you know, find the longest substring in common between these two. And we need a base case. So a good base case, if either string has length 0, just return 0. If one of these strings is empty, then the longest string in common between the two is a string of length 0. Right? There's no characters in common. So coding this is a little horrifying in C, right? Because this business of removing the last letter from a string is you know, like shaving a gorilla. Got to be careful. But nonetheless, I've coded this up. So you know, we'll input two strings. We'll get rid of the new line at the end. And then let's call longest common string, and I am passing to my LCS not just the strings but also the length of the strings, because this gives me a convenient way to truncate a string. I'll just say the length is one less than it actually is, and I won't require these strings to be null terminated. Alright, so LCS takes a pair of strings and a pair of lengths, and here's my base case. If either length is less than or equal to 0, I'll just return 0. Alright, and then I'll say working on, and I'll show the strings that I am currently working on. And I have my own print function here because, again, these strings are not null terminated. And then here's my two cases. So the first case, see if the two strings end with the same character. So if the last character, which is the length minus 1, is the same, then I'm going to return 1 plus the longest common substring of these two truncated strings. And I'm truncating them by just saying the length is, you know, the original length minus 1. So that's doing this piece, right? That's finding the longest common string of these strings where I remove the last character. And then I just add 1 because the last character will also be in common. All right. On the other hand, if the last character is not the same, then we have two possibilities, right? So we find the longest common substring between the original A and the truncated B, and the truncated A and the original B. So that's these two cases, opposite order. But take the first character and throw away the last letter, find the longest common substring between that and the second string, and vice versa. And then return the largest of those. So if return 1 is bigger, I'll return 1, otherwise return 2. Oh yeah, it's been a while. All right, so I mean this is really short code, right? There's a lot more code involved in setting this up, and you know, making my own print function that prints these things out because they're not null terminated and so on. But you know, it's basically 3 lines of code. If the last character is the same, return 1 plus the length of this common substring calculation. Otherwise, return the largest of these two calculations. And so this, you know, does a lot of work comparing strings, and it eventually found a common substring of length 6, which I don't remember what I typed in. If we want to actually record if we want to find the longest common substring, that gets a little harder. But algorithmically, right, in this case, the longest common substring would be whatever the longest common substring here was, plus 1 more character at the end, which was the last character from S1 or S2. Here we would return as the longest common substring whatever the common substring is we get back from either this or this, whichever one is greater. So this is kind of like, adding the inventory information to the max val information for knapsack. So my LCS now returns a character array, a string, um, and I've got some evil memory allocations in here. I've got all kinds of memory leaks in here too. But if either one is less than or equal to 0, the longest common substring is empty, so I just return something with a null terminator. Otherwise, see if the last character is the same, and if they are, let's find the longest common substring between the truncated strings, and then I go ahead and I just copy the last character of one of those strings into the last character of my return string, and I return that. Otherwise, call LCS and save the return values and return the longest, based on which one has the longest string length. I don't know. And you can see that there's a lot of recursion going on here, right? Two relatively short strings, but there's the tree of recursive calls branches pretty fiercely. I probably should have picked a shorter example. So we can speed this up with dynamic programming. So we'll let that continue working. So here's the dynamic programming version. I have a save array of 100 strings. So I'm assuming my string length is bound by what am I doing here? Yeah, this one's a little quirky. This works, but I don't think it should work. So we won't talk about that. If you wanted to implement dynamic programming, what you really need to do is you need to have some kind of cache that lets you put in two strings and gives you back the longest common substring in common between those. And I cheated and did this just by the length of these strings, but I don't think that's valid. So, but you would need to basically record, hey, when I find these two strings, here's the longest common substring. And what you're trying to do is deal with the fact that, you may be doing the longest substring between J, H, and K multiple times, right? We did it up here, and we're doing it again here. And to find the longest common substring between J, H, and K, I had to find J and K, right? And so you save that result the first time, and you don't have to recurse successive times. And most of these calculations we'll find have been done before. And so if you save those, right, you prune your search tree. But to save the caching information on this, maybe you want to use a hash. Right, take these two strings and use them to find an index in a hash table or something like that. But it's still going to be a big time savings compared to this. So let me. All right, so that was a shorter one. All right, does this make sense? Like I say, the implementation, don't worry about, because C is just not really good with strings. But algorithmically, questions about this? I'm going to say don't worry too much about the caching on this one because the caching is really strange. But in general, when we want to put in dynamic programming, remember we're doing the same thing in all cases. Basically, right, I called this blah yesterday. Blah is all of this for this problem. It's all the work that you do. So we're trying to find the longest common subsequence of two strings. And we do blah, and we return, you know, whatever the answer is. So to add dynamic programming to this, what we want to do is we want to say if our cached, you know, memory of S1, S2 is valid, then just return cache S1, S2. Otherwise, do blah, figure out your answer X, and then save that in our cache of answers, and then return X. And so these are the pieces that constitute the dynamic programming aspect. If our argument to our function is a simple integer, and the result is an integer, then our cache is an array of integers, and we index it off of the argument. So with Fibonacci's, we had an array of 1,000 integers, and if we wanted to find fib n, we just checked our save array bracket n, right? It's just a little harder for this one because our arguments aren't integers and we have two arguments, right? And they're strings, so we need to, you know, index our cache with a pair of strings. And that's why we're probably talking about a hash or something. But yeah, for PA5, blah is the max val function, the calculation of all of that. So the loop that goes through and calculates each of these things, right? That's blah. And in the very beginning, before you start doing all of this, you check your cache and you say, oh yeah, I've already got a value for 4, right? And so you just return that. And if you haven't done this calculation for a capacity of 6 yet, when you're done, you save this result somewhere associated with capacity of 6. And then you can just read it out of there next time someone asks for max val of 6. All right, other questions about this? How can we check to see if we already calculated something? So the most straightforward way would be, instead of making an array of integers, make a structure. We could call it cache entry or, you know, answer thing or something like that. But we could include a field in there called valid that we initialize to 0. And when you put something into your cache, right, in addition to saving the answer, you also set the valid flag to 1. And so you want to know if this cache entry is valid, just check to see if the valid flag is 1. Now we shortcutted that with Fibonacci because we know our Fibonacci numbers are always positive. So when we did the Fibonacci example and we had our save array, we just initialized all the answers to 0. So we simply had an array of integers, and if the integer value in the array was 0, we knew it was not a saved value. And we had to do blah, calculate the Fibonacci number, and then load that saved value, which would be positive, into our save array. The next time we look for that Fibonacci value, we would look at the value, we'd see it's positive, okay, this must have been a saved answer, and we just read it out of the array. And you can do that with max val also, because your max vals will never be negative. Now your max val could be 0, but if it's 0 and you recalculate it, it's not going to be a problem, right? It's not going to go any deeper in the recursion. So you can get away with this for your max val also. But once you're doing the item counts, right, you're going to need a structure anyway. And so you can go ahead and, you know, have a valid flag and then have either an answer and an array of item counts, or, you know, another struct. This would be like a struct answer, the answer. So is caching almost always using a hash? Not necessarily, although, you know, an array is kind of a hash, an array of integers. But it's using something that lets you look up a value based on, you know, some sort of index. With Fibonacci, our index was just the number that we were trying to find, you know, that nth Fibonacci number. In this case, you know, it's a pair of strings, so yeah, we probably want something like a hash, an associative array. For max val, the argument to max val is just an integer, so we can use that as an index into our cache. So you don't necessarily need to be hashing. A hash is an associative array, so we can say, you know, x bracket 5, x bracket 0, x bracket 1, that's a plain old array, right? With a hash, we can say something like x bracket hello, x bracket 1, 2, 3, x bracket, you know, whatever. We can, it's an array that can be indexed with something more than just consecutive integers starting from 0. All right, so an array indexed with an integer starts from 0, goes up to the length of the array minus 1. An associative array we can index off of anything, and we usually show it with strings, but this could be any type of any piece of information. It could be a binary string, it could be a compiled C program, it could be a JPEG file, or a snippet of a piece of music, right? And so that's where we get into a hash, right? We need a way to take this thing that's not a simple integer and turn it into something that lets us find the piece of information that we've got stored at that index. All right, other questions? And for this one, I think the more relevant part is this algorithm itself, right? Rather than how we would actually store these values and retrieve them. And we're not going to code this up, right? But it's another example of the kind of recursive algorithm we're seeing in knapsack and in rod cutting. And it's just a really powerful way to think about problems. For the max val problem for PA5, yeah, you can save your max vals in an array. Initialize your array to zeros. Since we know the maximum capacity we're interested in is 1024, you can make an array of 1025 integers, initialize them to 0, and any time that you calculate max val of 17, check to see if element 17 in your array is non-zero. If it is, that must have been saved by a max val calculation, so just return element 17 of your save array. But if element 17 is 0, we need to actually calculate max val 17 by going through the for loop, doing the recursion. But when you're done, before your final return, save your answer into your save array bracket 17. And the next time someone wants to know max val 17, they'll just read it out of the array instead of calculating it. All right, we'll throw eggs off buildings tomorrow. Do one more example of this kind of heavy recursive algorithm with an egg drop problem. So we'll do that tomorrow. Talk about any final questions on PA5. And have a good afternoon. All right, see you next time.